Welcome, welcome, welcome. In this video, we're going to discuss one of my favorite problems that has to do with coding theory. It's called the camper's problem. So it goes like this. A counselor has 8 campers with her at a junction. So the junction is right here, and they've been wandering around, exploring things, and they've come back to this junction. And they know that their camp is 20 minutes down one of 4 possible paths. So path 1, path 2, 3, and then there's the 4th one. Is the camp there, or possibly there? And it's going to be dark in 1 hour, and the group must find their camp before dark. Now, they know that they've been to this junction before, and when they left the camp to get to that junction, it took 20 minutes. So the correct path will take 20 minutes to travel down to the camp, and I guess 20 minutes back if you like. So what they can do is divide and conquer at this point and check 20 minutes down each of the paths, and then all reconvene back at the junction, decide where the correct camp location is, and the counselor can take everyone to the camp. And it's going to be dark in an hour. If they wait too long, after an hour, there's going to be creatures out here that are going to get them. So they really do have to get back safely in time in 1 hour. But there is a problem. You can't just divide and conquer and leave it at that, because 2 of these buggers have been lying to the counselor. And unfortunately, the counselor doesn't know which 2 of the 8 are lying. And they don't always lie. It's just a sometimes lie. So sometimes there's been lies in the group and sometimes there hasn't. We know that at most 2 of them will lie and the rest will tell the truth. So our objective is how to find the camp. What can the counselor do to split up campers and then reconvene back at the junction to guarantee that no matter who lies or if they lie, the counselor always knows where the actual camp location is. So pause the video now, try to think about a solution, and then we'll talk about what the heck this has to do with coding theory right away. Okay, so if you came up with the solution that the counselor should check one path and divide the campers up evenly among the other paths, you would be correct. So 3 campers down one, 3 campers down another, 2 down another, and then the counselor individually checks one of the paths. So, for example, the 3 campers that went down path 1 could return and say, yes, the path is correct, and yes, the path is correct, and then maybe the final one says, no, that's not where the camp is. So at that point, you don't know who to trust. Then maybe the other 3 that were down path 2 all say no, and maybe there's some disagreement on path 3. So here you would know that there's a lie on path 1, and there's a lie on path 3. And there can only be a total of 2 lies. So you can believe the majority on path 1 and say, okay, yes, it's down path 1. And of course, there's other scenarios to look at. Maybe the first path was no, no, yes. And then the next path was no, no, no. And then the final path was no and no. Well, there's a disagreement on the first path. So as soon as there's a disagreement on the first path, you can trust the majority on path 2. And there's agreement on the last path. So there couldn't have been 2 lies here because one of the lies has already occurred here. So we get to trust the last path. So in this case, we trust what was said here, all no's, and we trust what was said here, all no's. So the path 1 must be the correct path that contains the camp. Let's look at one more scenario. Let's say everyone said no. In this case, you can trust what's said on path 1 and path 2, because we can't have 3 liars. So it's not down path 1 or 2, so it must be down path 3. Now, of course, this is not a proof. We just looked at some random scenarios. But the neat thing is we can use coding theory to give us a proof. We'll do that on the next page. So we'll answer the question of why does this always work? So the objective here is to design a code that will enable the counselor to figure out where the camp is. So we'll think of a sender-receiver team here. So the counselor at the beginning of the problem, so we'll say at the 0-minute point of the problem, is going to be the sender. And a message is going to be sent out to the counselor at the 40-minute point in the problem. So this counselor in the future point of our problem has to get a message and do some error correction with that message. So the counselor always checks one path alone. All the other paths have campers going down them. The counselor would never want to take a camper with him, because what if, sort of worst case scenario, that camper just lies to her face and then information is lost. So she's going to do the split up that we talked about earlier, the 3-3-2 split up. And we'll design a code. And in this code, we're going to use 1 to represent yes and 0 to represent no. That's a common choice. And these 1s and 0s are going to be called bits. So those are the symbols that we use in each of our words. And we always start from the truth. You always make your code word the accurate truth that you want. So code word 1, if the camp is actually down path 1, then the campers in order will say this: 1, 1, 1, 3 1s, and then a bunch of 0s. So all of these ones will say yes. Then the camp is down path 2. The middle ones say yes. Path 3, only the last group says yes. Now, let's remember, anytime we design a code, if we're thinking about trying to correct a digit error, what we want to know is what the Hamming distance is. That will help us deduce how we're doing with the digit error. So our Hamming distance is 5 or more. Let's check that. So the distance between the first pair of code words is 6. The second pair of code words here is 5. And then the last combination, the first one and the last one, has a Hamming distance of 5. So the smallest number here out of those numbers, the smallest pair, has a Hamming distance of 5. So our minimum Hamming distance for this code is 5. So if we want to find out how much we can correct, we'll set 2n plus 1 equal to the minimum Hamming distance, solve for n, and we get 2. So that means that this code that we created can successfully correct 2 errors. And therefore, in every possible case, the counselor can deduce the correct location of the camp. Either she finds it herself, or she does the error correction at the 40-minute point to accurately deduce the location of the camp. So I think it's nice to kind of draw a picture of this. So let's draw a Venn diagram to sort out what this looks like in our heads. So if we go to the next page, we notice that these code words have been put into a nice diagram for us. So the middle of each of these circles represents the code word. The circles in this diagram represent all possible 2-digit errors. Now, if you notice in the picture, we didn't write every possible error just because the diagram would get a little bit ugly, but we wrote some sample errors that are floating about here. And the idea is, if the truth starts right here, and we have 2 campers that could possibly lie, that lie could travel us to an errored code word somewhere in this circle, but we would always be able to correct things back to the middle of the circle. There would be no confusion about which circle we're in. If you started in this circle, you could correct back to the middle, and the same with path 2. And of course, there are some scenarios like this that would never occur because the Hamming distance is too big. So with only 2 liars, that sequence here would never occur. And that sequence is the same thing. And the same thing with, it's impossible for everyone to say yes. Okay, so now that we've got everyone safely back to the camp, we have another problem. So some mini marshmallows have gone missing. The camp director found that these mini marshmallows had been stuck up 5 junior campers' noses. So I'm sure you're all very curious to show that there must be a group of 3 junior campers with a combined total of 3 or less marshmallows up their noses. So this might seem like a weird problem to ask, but these junior campers are going to teach us something about the campers problem that we just looked at. They're going to teach us how to find the minimum number of campers that we need. And what we'll talk about here is a little bit of an extension to the pigeonhole principle. This is a show that there must be this existing scenario here. It's kind of like a pigeonhole principle style problem where marshmallows are being assigned to noses. So let's set that up. So we have 7 marshmallows that are representing pigeons that are flying into 5 junior campers' noses. So what does the pigeonhole principle tell us? So by the pigeonhole principle, one junior camper has 2 or more marshmallows. So the problem was talking about a group of junior campers. There's a way that we can get a statement about a group of the junior campers by noting that, okay, if one of them has 2, let's think about that. So let's get out our green pen and say, okay, this one here, just for example, has 2, and it's 2 or more. They could have gotten all the marshmallows up their nose. We don't really know. But what it means about the rest of the junior campers, there's an equivalent statement to the usual statement that we use with the pigeonhole principle. And that equivalent statement is that the other ones must have 5 or less. Well, there's 7 in total, and that's how the distribution goes. So let's write that equivalent statement down. So our 4 junior campers have 5 or less marshmallows. So that's a perfectly accurate statement to say. That's completely true. Now we might want to go directly to this statement in the future and maybe skip the general way that we described the pigeonhole principle to begin with. So let's think of a formula that we could come up with, this number 5 in the future. So we could take the grand total of marshmallows, which is 7, and we could subtract the number from above, which is the average marshmallows per camper rounded up. So that's how you could get to the or less number directly. Okay, now this didn't quite tell us what we want. The question was about a group of 3 junior campers, but now we have a group of 4 junior campers. But they're being distributed 5 or less marshmallows. Well, now we can set up the pigeonhole principle again to make that assignment. Let's draw a picture. So now we have 5 or less marshmallows being distributed as pigeons to fly into 4 junior campers. So we can make a similar statement from above. 3 junior campers have the total of 5 minus 5 divided by 4 rounded up, which equals to 3 or less marshmallows. And that shows exactly what the question asked for. And just a comment before we move on. This does say 5 or less. So if 5 or less fly into these 4. It could be 5 or 4 or 3 or 2 or 1 or even 0 marshmallows. So the or more statement from above wouldn't make any sense, or at least there's no value in saying, one of these junior campers has 0 or more marshmallows. But the or less statement is still perfectly valid, because the largest possible number that could fly in is 5, and this number can only go down. So this number here could be 3 or less, or 2 or less, or 1 or less, but 3 or less is still perfectly valid in all of those cases to cover them all. Okay, so we'll use what we've learned here to help us prove that the camper's problem was solved in its most efficient way. So we're going to prove that the camper's problem cannot be solved with any less campers. 8 is the minimum. And you probably guessed it already, we're going to start off this proof by using the pigeonhole principle. So we've got our 7 campers set up here, and the 3 paths that we have to distribute them to. Remember, the counselor eliminates one of the paths. The campers are going to represent pigeons, and they're going to be distributed to the 3 paths. Let's think about the other way that we equivalently related the pigeonhole principle in that what was taught to us by the junior campers. In other words, the or more statement. Let's use that one. So we can say that 2 paths have the total number of campers minus the average number of campers per path rounded up, which is 4. So 2 paths have 4 or less campers. So now we're going to try to prove that we cannot solve the camper's problem. So we'll start by assuming that we can solve the camper's problem. So if we can solve the problem with 7 campers, then there is a code that we can build with 7 campers that will have error correction, where we can correct it back to the truth, the correct path that contains the camp. So let's write that down. Okay, so the question would be, how to make this code. There's many options for designing a code. So we're going to consider all possible codes that could be made. So our code is going to have 3 code words, one representing yes, the camp is down path 1, and then yes, it's down path 2, and yes, it's down path 3. And we have 7 pieces of information to help us out with that, the campers, that can either say yes or no, and we'll do the same as before. 1 is yes, 0 is no. And we don't know how many we're sending down path 1, just that when they come back, they'll say yes. So there's a bunch of 1s in, let's say, a first group here. And then afterwards, there's a bunch of 0s, because the rest will say no, the ones that went down path 2. And then the final group will say no as well. Okay, so once again, here we're representing, these are all the campers that went down path 1. They would come back saying yes. These are the campers that went down path 2. They would say no. And the final group that went down path 3 would also say no. And we're writing ... because we don't know how exactly we're going to distribute them. We're thinking about all possible distributions. So for path 2, we would have a bunch of them saying no first off, and then if they're telling the truth, they would say yes afterwards, and then the final group would say no. And then path 3, similarly, first group would say nope, next group would say nope, not down that path, and then final group would say yes, down that path. Now, of course, this is if everyone is telling the truth, and we have to think about whether we can do error correction here. But there is something in addition that we know. We know that no matter what, 2 paths have to have 4 or less campers. So let's assign path 2 and 3 to be those paths. So this chunk, that amount, has to be 4 or less. Okay, now let's try to think about the minimum Hamming distance. Well, we don't know exactly how everything is distributed, but we do know between path 2 and 3 that there's 4 or less campers there. So the Hamming distance, if we write h of the code word path 2, comma, path 3, that represents the Hamming distance between those two, and the Hamming distance is 4 or less. We don't know if it's 4 or 3 or 2 or 1, but what this means is that the minimum Hamming distance, the smallest Hamming distance that we can possibly find, is also 4 or less. So now we know that every possible code that we make has a minimum Hamming distance of 4 or less. And the issue with having the minimum Hamming distance of 4 or less is the error correction cannot be done. So we would need to be able to correct 2 errors. The errors are equivalent to the liars that we would need to correct, and we just don't have enough to do that because the magic number for error correction to correct these digit errors is 2n plus 1. So our n value in this situation is 2, so let's plug in 2 right there. And that number there is 5, and that's bigger than the Hamming distance, or our minimum Hamming distance, that any code will build for us. So we won't get the error correction that we need. And in conclusion, this means that the campers problem cannot be solved with 7 campers. So we have a contradiction. I'll give it the lightning bolt, get struck down there. Our assumption is wrong, and we must have 8 campers at a minimum to solve the campers problem. So I strongly encourage you to think about what the minimum number of campers would be if you had n possible liars. So you can generalize this idea, and there's not very much you have to change to generalize the idea. You can pretty much go through the same thought process that's in this entire video to generalize the number 8 campers with 2 liars to 3n plus 2 campers with n liars. So thanks so much for listening. Thanks for checking out the video. We'll see you on the next one.